Look around, and you will see a world defined by constraints. Space, time, and money fluctuate wildly, but beneath all of it lies a single, invisible grid that holds it all together. The Cartesian coordinate system functions as a computational engine, translating physical constraints into an algebraic workspace where complex problems become solvable. Take a simple straight line drawn between 2 points. Within this basic geometric shape lies the mathematical DNA to decode multidimensional problems across entirely different fields of study. By mastering the geometry of this straight line, we can build rigorous mathematical models for everything from economic pricing rates to the area of physical land, straight through to the solid volume of three-dimensional objects. To see how this engine works in practice, we will start flat. We will map simple rates of change over time, and step by step we will build up to constructing physical reality. Coordinate geometry acts as the ultimate translation tool, converting the unpredictable chaos of the real world into clean, perfectly solvable algebra. Let's begin with a standard business scenario. A company tracks the selling price of a mobile phone over a 1-year span, from March 2019 to March 2020. This graph plots time in months along the x-axis against the phone's price in rupees along the y-axis. Because the initial price point is high, we use a zigzag cut on the y-axis to skip the empty space from 0 directly to 8,000. The x and y-axes do not have to scale at the same units, they just have to remain consistent. For the first 4 months, the price holds steady at 8,000 rupees. Mathematically, a constant, unchanging rate always translates to a perfectly horizontal line. Then demand spikes. The company increases the price by 250 rupees every single month until January. This specific rate of upward change is what we call slope. To find the exact algebraic equation for this growth, we only need to identify 2 coordinates along the path, like month 5 at 8,500 and month 7 at 9,000. Plugging these values into the 2-point form locks in the mathematical formula for the entire upward trend. But in January, a competitor launches a cheaper alternative, forcing our company to aggressively drop their price by 500 rupees a month. This negative rate of change directly translates to a negative slope on our grid. We plot the drop from January to March, giving this segment a slope of negative 500. You see this exact same linear logic in standard cell phone billing plans. A fixed monthly fee acts as a static y-intercept, while the per-minute charge acts as the slope, pushing your total cost linearly higher. By connecting these distinct phases, we create what is known as a piecewise function. Even when market behaviors drastically shift, graphing these connecting line segments allows us to accurately model and predict precise financial outcomes. We can apply that same grid logic to physical space. Imagine a triangular plot of land that needs to be watered and fenced. This diagram maps the field's boundaries onto a coordinate plane, anchoring the corners at exact vertices, 1, 1, 9, 1, and 1, 7. Look closely at points A and C. They share the exact same x-coordinate of 1, which means the line connecting them is perfectly vertical. Points A and B share a y-coordinate of 1, making that line perfectly horizontal. Where a vertical line meets a horizontal line, you get a strict 90-degree angle. Because the coordinates prove this is a right triangle, we can use the basic formula for the area of a triangle, half the base times the height. Calculating that physical area yields exactly 24 square units. If we are given the cost to water per square unit, we simply multiply it by the area to find our total expense. Now consider the perimeter. To calculate the cost of wrapping this field in 3 rounds of wire fencing, we need to know the exact length of the outer boundary. We already know the straight vertical and horizontal sides measure 6 and 8 units. For the angled boundary, the hypotenuse, we apply the Euclidean distance formula. By calculating the square root of the differences between our coordinates, we find the diagonal length is exactly 10. Adding 6, 8, and 10 gives us a total perimeter of 24 units. We multiply that perimeter by our 3 rounds of wire and the price per unit to lock in the final cost. By anchoring physical boundaries to a coordinate system, we can mathematically derive exact dimensions and total project costs directly from 3 known points of data. This chart shows a classic physics problem translated into geometry. Two individuals, Abdul and Ram, start at different locations, Abdul at -2, 2, and Ram at 4, 10. They are moving directly toward each other. Abdul is moving at 60 kilometers per hour, while Ram is moving at 90 kilometers per hour. We know they will meet on this path after exactly 4 minutes. We need to find the exact coordinates of their meeting point, but we want to do it without relying on complex, time-dependent calculus equations. Because their travel time is identical, the ratio of their speeds is exactly equal to the ratio of the distance they cover. 60 to 90 simplifies to a distance ratio of 2 to 3. The meeting point simply divides the physical path in that exact proportion. To solve this geometrically, we use the section formula. By plugging our 2 to 3 ratio into the starting coordinates, we calculate the exact point of intersection at 0.4, 5.2. The section formula works by applying that 2 to 3 ratio to the x-coordinates and the y-coordinates entirely independently, triangulating the exact physical location. A standard distance time graph only tells you when an event happens. This spatial approach maps the actual physical movement across a rigid landscape. This geometric framework provides a static model for dynamic motion, allowing us to solve for position by analyzing spatial ratios of constant speeds. We can push these coordinates further and move from flat planes into solid space. Take the linear equation, 7y equals 56 minus 8x. The fastest way to anchor any line is to calculate its intercepts. Setting y to 0 gives us an x-intercept of 7. Setting x to 0 gives us a y-intercept of 8. Connecting 7, 0 and 0, 8 draws our boundary in space. We can manipulate this space by treating the y-axis as a physical mirror. To create a reflection, we simply invert the sign of the opposing coordinate. The point 7, 0 flips to -7, 0, generating a mirrored boundary that encloses a rigid triangular area on the grid. Now we make the leap into the third dimension. We start with a single line segment anchored at the origin and extending to the point 4, 3. If we rotate this two-dimensional line a full 360 degrees around the x-axis, it sweeps through empty space, leaving a continuous trail that forms a solid three-dimensional cone. This is a volume of revolution. The original two-dimensional coordinates serve as the exact blueprint for the solid object. The x-coordinate establishes the physical height of the cone, and the y-coordinate dictates the exact radius of its circular base. By carefully anchoring points on a flat grid, a simple two-dimensional line segment dictates the precise geometric instructions required to construct complex physical volumes. Look at the models we just built side by side. We mapped the piecewise fluctuations of market pricing, we plotted the precise physical intersection of two travelers, and we generated a solid physical volume out of thin air. These look like problems from completely separate fields of study: economics, kinematics, and architecture, yet they all share the exact same underlying mathematical logic. Coordinate geometry serves as a universal framework for constraining, measuring, and predicting the physical world through the logic of the grid. The next time you encounter a real-world system governed by complex variables, do not get lost in the noise. Strip away the variables and look for the grid. Ask yourself where the origin point lies, and trace how the constraints map across the x and y axes. Because once you can translate a physical reality onto a mathematical grid, there is no problem you cannot solve.